Welcome to This Explainer. Okay, today we are unraveling a truly bizarre historical paradox. Have you ever wondered how a 17th century French theologian somehow managed to get his name permanently hard-coded into the digital architecture of the 21st century? I mean, it sounds literally like science fiction, but it is an absolutely real piece of mathematical history. So why is a 17th century monk in your code? It's a massive timeline jump to wrap our heads around, right? We are talking about a guy who wore robes and lived centuries before anyone even dreamt of electricity, and yet his name is firing away inside your laptop right this very second. How on earth did Mersenne cross hundreds of years of history to become a completely ubiquitous term in modern computer science? Okay, let's dive into this. Section 1, the human internet. So, living from 1588 to 1648, Mersenne wasn't just a theologian. He was this multifaceted philosopher whose scientific curiosity was, frankly, groundbreaking. He relentlessly studied music theory, specifically looking at exactly how strings vibrate. In fact, his deep mathematical analysis of sound actually earned him the historical title of the father of acoustics. You know, he was basically always out there looking for the underlying mathematical rules of reality. But his absolute most vital contribution? That was his network. We're talking Descartes, Galileo, Pascal, Fermat, literally the giants of history. Back in the 1600s, scientific journals just didn't exist yet, so Mersenne essentially acted as a human internet. He was constantly corresponding, carrying complex mathematical ideas, proofs, and arguments back and forth between these iconic thinkers. If you wanted a totally new theory tested in 17th century Europe, you routed it right through the hub. That was Mersenne. Now, what's really interesting about this next part, Section 2, decoding Mersenne primes. Shifting from his crazy networking skills over to pure math, we find his immortal formula. A Mersenne number is a positive integer that is exactly 1 less than a power of 2. The elegant little formula is m sub n equals 2 to the power of n minus 1. But, and this is a big but, for this result to actually be a prime number, the exponent n must itself also be a prime number. That's the golden rule here. So the absolutely crucial point is that while the exponent being prime is a requirement, it's not some magical guarantee. If your exponent n is 2, 3, or 5, which, are all primes, the formula works beautifully. It yields 3, 7, and 31, all prime numbers. But look what happens when n is 11. 2 to the power of 11 minus 1 equals 2047. Actually, scratch that. 2047 is not prime. It's perfectly divisible by 23 and 89. Mersenne figured out pretty quickly that finding these primes is incredibly elusive. And here is where the 17th century crashes headfirst into the modern era. Because Mersenne primes are so incredibly rare, today's computer scientists actually use them to hunt for the largest known prime numbers in the entire universe. Through the Great Internet Mersenne Prime Search, or the GIMPS project, computing these massive numbers pushes our modern processors to their absolute limits. To put that into perspective, the largest primes discovered by GIMPS today have tens of millions of digits. It serves as this brutal, highly practical stress test for computer hardware stability and processing power today. All right, let's drop down another level of the iceberg. Section 3, the Mersenne twister. So, down in the trenches of computer programming, if you see the name Mersenne in code today, it's almost certainly referring to the Mersenne twister. Designed much later, in 1997, this is a widely used pseudo-random number generator, or PRNG. Since computers are strictly logical machines, generating true randomness is exceptionally hard. The Mersenne twister became famous because it's incredibly fast and produces extremely high-quality randomness, which is absolutely vital for complex software simulations. And this brilliantly illustrates exactly why it carries his name. Just look at this massive number, 2 to the power of 1993.7 minus 1. That right there is a Mersenne prime, and it represents the algorithm's period length. Meaning, a computer using this generator will take exactly that many steps before the random sequence finally repeats itself. It's a mind-bogglingly vast expanse of randomness. Because of that unbelievable period length, it is utterly ubiquitous. Powered by Mersenne, it's the default random number generator in major programming languages and software. We're talking Python, Ruby, PHP, and MATLAB. Think about that for a second. If you have ever run a statistical model, played a video game, or literally just looted a web page powered by PHP, Mersenne's 17th century math was quietly rolling the digital dice behind the scenes. Crazy, right? Let's move to and see how this builds. Section 4, hunting primes with Python. Let's actually put this into practice. If you want to write a Python program to find these efficiently, it breaks down into 3 super accessible human steps. Step 1, check if your exponent n is a prime number. If it's not, stop right there. Step 2, calculate 2 to the power of n minus 1. And step 3, check if that resulting massive number is also prime using a standard primality test. If it is, boom, you found one. Just a quick tip, if you try running this code yourself, definitely keep your upper limit for the exponent n pretty low, like under 35. Because Mersenne numbers grow exponentially, your computer will literally freeze up trying to calculate the astronomical sizes of higher primes. So what would a 17th century philosopher think of powering the digital age's randomness? Mersenne was just trying to understand the mathematical fabric of his universe, and inadvertently he gave us the keys to build our digital ones. It really makes you wonder, what seemingly obscure abstract concepts being discovered right now will be hard-coded into the unimaginable technologies of the year 2400? Thanks for joining me on this explainer, and hey, keep exploring the incredible logic behind our world.
I hope you have seen the explainer. And I request before you come to this Python program for creating the Mersenne prime numbers, I request please just understand the concept. Once you understand the concept, then doing the programming will be very easy. And make sure you have taken some notes also, so that because student already know the prime numbers around the age of 11. I think it is introduced in class 4 and 5. I do not know the curriculum, but mostly at this age it is it is introduced. So, and further they just increase the complexity of the question, and they ask in a different way. All right, so let's understand in the Python program. First of all, like here only def means define. All right, here define, a function is defined. It is the user defined function, you can say. And you can say is underscore prime, and they have defined a function. That is the way how you are going to define a function. And please remember about the syntax, all right, where you have to put the colon, where you have to put the bracket, and please remember all this. So here is the standard helper function to check if the number is prime or not. And then here is the comparison. We are comparing the number, that number should, if the number is less than 2, because we are going to check above. All right, so make sure if the number is less than 2, then it will return the false. Else, okay, and it is just going to check. And the range means actually this is the for loop. Okay, it is the for loop which will go like this. So in other language you must have learned in different way, but here for I means it will start a series of the number. Okay, so this is the way how we write for loop. And in range, so the in the bracket whatever is mentioned, okay, whatever is mentioned, that is your range. And this here modulo operator is just used to check the remainder. Fine, if the number and numbers is divided, and if the remainder comes 0, all right, if it is 0, then it will return false, else it will return. Now again one more function is defined, that find Mersenne prime numbers. Okay, so here we have just printing the all the messages. All right, this is all just to understand why these are the important messages, because it will help you to understand the program. Even in practical exam, or if you get the Python project, if you explain all these things, so it becomes self-explanatory. And if you want to revisit the program also, then it is easy to remember that why you have used this line and what is the purpose of using this line. Now again we'll come to here why this loop is taken here. So possible exponent, all right, iterate through possible exponent wherever it is possible. Okay, so it will repeat it. And then first of all they are saying the exponent n, all right, the exponent n must be a prime first. Okay, so they are saying that it should be a first prime number. So if the condition becomes true, then only they are going to calculate this step. Actually this one, like Mersenne underscore number is equal to 2 asterisk asterisk n means 2 to the power n. Okay, this here the double asterisk, please make sure this is used for the power. Okay, see, once we write something in a mathematical form and in computer form, actually you can say that computer expression we write in the different way. All right, here we have written in this way. Now in this we are going to check, fine, and if it is the prime number, if it will check after this calculation, this is your main statement. All right, this is your main statement. And what we have to see, that's we have to set the upper limit. Okay, for the exponent we have to set the upper limit. All right, upper limit means till where you want. Okay, and if you want, you can mention more than 20 also, but here the moment if it is less than this, it will stop. Okay, so here we are taking, because grows exponentially. Okay, it will keep increasing. Okay, so here we are keeping the limit, let it be till 20. So the program, if you see, it is not very long program. Okay, only the thing you have to see the formula and the way you define the function. All right, so let's say once again, I hope I have not made any changes. Let me save again. So if you want to see this, this is the main program. And one more thing, um, let me see that if you want to know the line numbers, so I'm going to put the line numbers. Okay, so you will remember, you can also put the line numbers in your program, so that at least you come to know that you are on which line. All right, so including the remark and all, total we have almost 30 line. All right, okay, it is 30 line. So just remember that this is the final program. All right, and these all are just marks. So last two line also just remember, and I will include the document file also, docs file also, from where you can get the written explanation also, and you can revise also. So I'm going to run the program finally, and let's see in which way it is going to give the answer. So we are going to run the module, and you can say very well. Okay, it was the previous when it was run, and it is up to 20 only. So you can see that this is the n value. Actually in the program you have seen that how, and see actually the way 2 to the power n in the printing message we have put like this. Okay, and so this is the way it has checked up to 20, and then you can see that how very quickly it increases in the number. All right, so exactly it is that Mersenne prime number. It is used in in a different way. So this is the exact answer. Okay, if you want to see again, I'm going to run it. Just let's see, run the module, and now you can see. All right, now it's very clear. All right, that I have refreshed, and then you can see how well it has given the number. All right, so this is, sometimes it can be also in various exams they can ask, but again I will say, do not jump to the program directly. Try to watch that explainer first of all, take some notes, and then come to this program. Keep watching, remember to subscribe.